Bismillahirrahmanirrahim. Assalamualaikum and good day to everyone. Our topic of presentation is Sum of Two Squares Theorem. The presenter is me, BINTI WAHID ANUAR, and NAZWANI ZULKIFLI, and NURUL AINA ATHIRAH binti OTHMAN. Our theorem says a positive integer n is the sum of two squares if and only if each prime factor p of n such that p congruent to 3 modulo 4 occurs to an even power in the prime factorization of n. Let's prove this theorem. First, we let n equal to s squared times m for some s and m are in integer z where m is a square free. In mathematics, square free is an integer which is divisible by no square number other than 1. That is, its prime factorization has exactly one factor for each prime that appears in it. For example, 10 equal to 2 times 5 is a square free, but 18 equal to 2 times 3 times 3 is not, because 18 is divisible by 9, which is equal to 3 times 3. Suppose that each prime factor p congruent to 3 modulo 4 occurs to an even power in the prime factorization of m. Then, m are not divisible by p. Thus, each prime p greater than 2 that divides m satisfies that p are congruent to 1 modulo 4. There is a theorem that says each p greater than 2 can be written as sum of two squares. Hence, the product of integer that can be written as the sum of two squares m can be written as the sum of two squares. Thus, since m can be written as the sum of two squares, m equal to x squared plus y squared for some xy in integer z. When we substitute m into the formula that we assumed before, which is n equal to ms squared, we substitute m, then we get n equal to x squared plus y squared times s squared, and we factorize it, we get sx squared plus sy squared. So here we show that n is the sum of two squares. Okay, since n is the sum of two squares, suppose that n equal to x squared plus y squared. Okay, if m equal to 1, then n equal to x squared. So each prime p in the factorization of n such that p congruent to 3 modulo 4 occurs to an even power. Now, assume m is greater than 1. We will show that for every odd prime p such that m are divisible by p and p are congruent to 1 modulo 4. Observe that x, y can be written as follows. X equal to dxy and y equal to dx2, where x1 and x2 are relatively prime and d are equal to greater common divisor x and y. Then we have that by substituting x and y into n equal to x squared plus y squared, we get this as squared m over d squared equal to x1 squared plus x2 squared. Since m, we said before, is square free, and s squared are divisible by d squared, with s squared equal to t times d squared for some t in z, integer z. So, tm are equal to x1 squared plus x2 squared. Then we know that m are divisible by p, so tm, which is equal to x1 squared plus x2 squared, are divisible by p. Thus, we have the congruence x1 squared plus x2 squared are congruent to 0 modulo p. So, x1 squared are congruent to negative x2 squared modulo p. By we move the x2 squared to the right side, we will show that p are congruent to 1 modulo 4. Assume for contradiction that p are equal to 4k plus 3 for some k in integer z. Then notice that p minus 1 equal to 4k plus 2, and by factorizing we get 2 times 2k plus 1. So we have originally x1 squared are congruent to negative x2 squared modulo p. Then we adding power with 2k plus 1, we will get x1 to the power p minus 1 are congruent to negative x2 p power p minus 1 modulo p. Now, notice that since x1 and x2 are relatively prime, p cannot divide both x1 and x2. Suppose x1 are divisible by p and x1 squared, then x1 squared are divisible by p also. We know that tm are divisible by p, so tm minus x1 squared, which is x2 squared, will be divisible by p. Since p is prime, x2 and x2 divisible by p, it is contradicting with greatest common divisor. X1 and x2 are equal to 1. Thus, x1 and x2 cannot be divisible by p. By applying Fermat-Little theorem say if p is prime and a positive integer such that a are not divisible by p, then a to the power of p minus 1 are congruent to 1 modulo p. Then we have x1 to the power of p minus 1 is congruent to x2 power of p minus 1 congruent to 1 modulo p. So we get that 1 are congruent to negative 1 modulo p, contradicting p greater than 2. Thus, p are congruent to 1 modulo 4. There also another theorem that we get while browsing the internet, where we can use it to find whether the integer is the sum of two squares or not, which is an integer greater than 1 can be written as a sum of two squares if and only if its prime decomposition contains no prime congruent to 3 modulo 4 raised to an odd power. Alright, we will explain more about this theorem by giving you some example that we have solved.
Hi, Assalamualaikum. My name is NAZWANI binti ZULKIFLI. I would like to present the example of sum of two squares odd number. Example number 1. Number 117. Okay, we know that 117 can be expressed as 3 to the power of 2 times 13. Okay, we know that the odd prime 3 is congruent to 3 mod 4 and have an even power. The odd prime 13 is not congruent to 3 mod 4 and have an odd power. This suits the theorem, which is each prime factor p of n such that p congruent to 3 mod 4 occurs to an even power in the prime factorization of n. So, we can conclude that 117 can be written as a sum of two squares. Okay, we go to the next example. Example number 2. Number 405. 405 can be expressed as 3 to the power of 4 times 5. We know that the odd prime 3 is congruent to 3 mod 4 and have an even power. The odd prime 5 is not congruent to 3 mod 4 and have an odd power. Hence, we can conclude that 405 can be written as a sum of two squares. Next example. number 1111. 1111 can be expressed as 11 times 101. Here, both primes have an odd power. 101 is not congruent to 3 mod 4, but 11 is congruent to 3 mod 4. So, for this number, 1111 cannot be written as a sum of two squares. The example number 4. Number 24505. 24505 can be expressed as 5 to the power of 1 times 13 to the power of 2 times 29 to the power of 1. 5 is not congruent to 3 mod 4 and have an odd power. 29 also not congruent to 3 mod 4 and also have an odd power. 13 also not congruent to 3 mod 4, but 13 have an even power. So what we can conclude here is 24505 cannot be written as a sum of two squares. Thank you.
Okay, next we move to the next example. Is 900 expressible as sum of two squares? Okay, firstly, we have to factor this into prime, right? So we'll get 2 square times 3 square times 5 square. As we can see, all of this prime is to the power of even prime, right? So we must check one by one. Okay, 2 is partial even prime, so 2 is congruent to 2 mod 4. 3 is congruent to 3 mod 4, but 5 is not congruent to 3 mod 4. So that we can conclude this 900 cannot expressible as a sum of two squares. Okay, next example is 584,820 expressible as sum of two squares? If yes, write the answer as sum of two squares. So firstly, we have to know either this integer is sum of two squares or not. So let me check. So firstly, we have to factor it into prime and we'll get 2 square times 3 to the power of 4 times 5 times 19 square. We have prime 3 prime with even power and 1 prime with odd power. So we know that 5 is not congruent to 3 mod 4 and 2 is congruent to 2 mod 4, which is special even prime. 3 and 19 are congruent to 3 mod 4. We can see all of this prime is fulfill the theorem. So we can say that 584,820 expressible as sum of two squares. So we have to write the answer as sum of two squares. From last slide, we know that this integer is the sum of two squares. So what we can do first is we write this as sum of a square. So it will be like this. 2 square is equal to 2 square plus 0 square. 3 to the power of 4 is equal to 9 square plus 0 square. 5 is equal to 2 square plus 1 square. And 19 square is equal to 19 square plus 0 square. Okay, note that each of these prime p being equal to 2 or of the form 4k plus 1 can be written as the sum of two squares. Now the identity is this formula. So we will solve this equation by using this formula. First, we solve these last two. Okay, so 2 as A, 1 as B, 19 as C, 0 as D. Right, so when we multiply this, and we'll get this answer 38 square plus 19 square. Okay, we bring it this down. Next, we solve the last two. We repeat the same step. Okay, so we will get 342 square plus 171 square, and we bring it down. Okay, last step, using the same formula, we will get 684 square plus 342 square. So the conclusion is 584,820 is equal to 684 square plus 342 square. That's all from us. Thank you everyone for the attention in watching our video presentation. Now we are open for Q&A session. Anyone have any inquiries can unmute your mic. Thank you.